In this module, we will discuss conjugation and conjugate symmetry property of continuous time Fourier transform. So taking the complex conjugate of xt has the effect of complex conjugation and the negative omega on the corresponding Fourier transform. This is what we expect because we are already familiar with the properties of continuous time and discrete time Fourier series. Once again, we are not going to derive this property. In fact, the derivation is very simple and straightforward. It is given in the book. All we have to do is to write down the Fourier transform equation and then take the conjugate on both sides, followed by the replacement of omega with minus omega, and that's it. So what we will do next, we will discuss some important consequences of this conjugation property. First of all, if xt is real, it means that xt is the same as its conjugate, and therefore we can very easily show that xj omega, the Fourier transform of a real signal, is conjugate symmetric. What we mean by conjugate symmetry in this context, if the Fourier transform capital xj omega is a complex function with respect to omega, then we can write it down into its real and imaginary part, or into its magnitude and phase form, and then we can very easily verify that the real part of the Fourier transform and the magnitude of Fourier transform, they are even functions with respect to omega, while the imaginary part of the Fourier transform and the phase of the Fourier transform are odd functions with respect to omega. And there is one important consequence of this property. Whenever we are dealing with real signals, it is sufficient to compute or display the Fourier transform of real signals just for the positive values of omega. And you will see this in communication systems. Whenever we deal with whenever we are writing the Fourier transform of real signal, we just specify the Fourier transform for the positive frequencies, because this information is sufficient, and from this information we can reconstruct the complete Fourier transform if we know the conjugate symmetry property. Then in addition to xt being real, if it is also even, we can show that the Fourier transform of a real and even signal is also a real and even function with respect to omega. Similarly, if xt is real and odd function in time, then its Fourier transform is purely imaginary and odd function with respect to omega. And there is another interesting result. Any real signal can be written down as sum of even and odd functions, where the even component of xt is the sum of xt and its time reversed signal, and scaled by 1/2, and the odd component is xt minus the time reversed signal and scaled by 1/2. So based on the conjugate symmetry property and the results in A and B, we can easily show that the Fourier transform of the even part of xt is equal to the real part of the Fourier transform of xt. And similarly, the Fourier transform of odd part of xt is j times the imaginary part of the Fourier transform of xt. And here is a practice exercise. In this exercise, we consider 3 real signals from our previous examples. We have xt, which is one-sided exponential decay, yt, which is a double-sided exponential decay, and zt, which again is a double-sided exponential decay, but for t less than 0, the magnitudes are flipped. So I hope you have already computed their Fourier transforms. If you have not computed them, do it in this practice exercise and verify the conjugate symmetry as well as the subsequent properties A, B, and C that we discussed above. Xt has no symmetry. We can break it down into its even and odd parts. Yt, you will notice that it has even symmetry. We can also express yt in terms of xt. Similarly, zt is odd symmetric, and we can express it in terms of xt as well. And if when we compute the Fourier transform of yt, we will notice that the Fourier transform of yt is 2 times the real part of the Fourier transform of xt. And similarly, the Fourier transform of zt will be j times j, and there will be a scale factor of 2 times the imaginary part of the Fourier transform of xt. Why we are getting this factor of 2? Because yt, when you will express it in terms of xt, you will notice that yt is 2 times the even part of xt, and zt is in fact twice the odd part of xt.